What a time to be alive, to be learning about multivariable calculus and in particular about vector valued equations and vector fields like we're going to learn about today for two reasons. Basically, some of the two hottest topics, if you go maybe trending topics on X are the Artemis II mission and AI. And today I'll show you how this concept of vector fields is crucial in both cases. I find this image just so amazing that you can just review all of Calculus 3 just looking at this picture of how do you prepare for this? What are the calculations that you have to do to make this happen? And you have a trajectory. So this is a trajectory, it looks 2D, but it's a 3D trajectory. You have to take into account, you can see that it's not just a motion, go to the moon and back. It's a shot, it's a slingshot to make sure the moon is there when you arrive so that the moon gives you that loop, that gravity assist to come back. Otherwise, if you miss that, you'll go into space forever, right? So the stakes of designing something like this, designing a path, are so huge. And look how we can do it. How is this happening? We're going to see today that it would cost just a massive amount of gas, of fuel, to do this if it was just a trajectory to the moon and back without the gravity assist. So what you don't see here is that there is a vector field around us, which is the gravity vector fields. In this case, there are three main vector fields. There's one vector field of gravity forces, but there are three forces that are happening here, which is the force of Earth, the force of the moon, and the force of the sun to some degree, right? And you have to take those into consideration so that you are not trying to fight them all the way to the moon and back. You are trying to save fuel by using their forces. So what we're going to do today is actually set up an integral that determines how much fuel we're going to spend if we go in a certain path. Once you have that equation, then you can actually do a differential equation to solve for what is the best path that minimizes the amount of fuel that I'm going to do. So in all of this, what you see is that the NASA engineers have minimized the amount of fuel by maximizing the transfer of kinetic energy from the Earth to the Orion spaceship and from the moon to the Orion spaceship, so we don't have to pay for it, okay? Let the moon pay for it. Okay, so let me go back to vector fields, but I also mentioned AI, and we'll see that the same concept is used to train LLMs. When you hear, this model was trained on this data, what does that mean? And it is, again, a vector field that we're using, and we're doing a path in a vector field that is minimizing, in this case, the loss functions, the error that LLM is going to produce when you ask questions, okay? So let me go back. Vector fields. What is a vector field? Vector fields are all around us. There is vector fields, there's magnetic vector fields, there's gravity vector fields, there is wind happening. So a vector field is just going to be, we have some space, and then at every point in space, there's going to be a vector that is going to give me a direction, and it's a vector, so it gives me a direction and a magnitude of something that we're trying to measure. In this case, these are graphs of wind in the Bay Area. But they are everywhere, as I said. You can just see that you can just draw here vectors of where the hair is going on your head. And then you can see that there is a singularity there, that there is the vector field vanishes. It turns out that this is an image that you can find if you go on the internet and look for the hairy ball theorem. There are theorems that say things about vector fields. If this kid actually had hair all around the head, then the theorem would say that there is a point in the head where the vector field has to vanish like this. But in any case, so what is a vector field? In R2, a vector field is a function that assigns to every point a two-dimensional vector. So what that says is that we are going from R2 to, in fact, R2, in that for every point, it gives me a vector, and we represent that as in this picture, that every point has a vector attached to it. That is giving me, again, some force at that point, some wind or some direction of hair, and exactly at that point. And it's telling me two things. It's telling me in which direction this force is acting, and it's also what's the magnitude of the force at that point by computing the length of the vector. In R3, we have the same concept. So a vector field will go from R3, it sends a point to the vector at that point. So you can just visualize it in R3 in the same way that for every point in space, there will be some vector that is telling me something about a force or hair or what have you. Okay? So, for example, let's sketch a vector field in a plane given by f of x, y is x, comma, 0. You can start by giving you some values. So what happens at some points, and what is the vector field at that point? What is the vector at that point? I meant here the point x, y. So at 0, 0, you see that I get 0, 0. So the vector vanishes. There is nothing happening at 0. At 1, 0, I get 1, 0. At 2, 0, I get 2, 0. At 0, 1, I get 0, 0. At 0, 2, I get 0, 0. There's nothing happening. For points in the y-axis, there is no vector, or the vector vanishes at those points. But once I go to something like 1, 1, then I get 1, 0, or 1, 2, I get 1, 0, etc. So the way we represent this is we represent, and by the way, what is the size of each vector? The size of each vector is going to be given by the length of the vector. So it's the square root of x squared plus 0 squared. So it is the absolute value of x. Okay. So what I get, I'm going to have to chew on a candy. So what I get is that here, 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 all the vectors vanish. But then over here, I have a vector of 1 unit length. Over here, I have a vector like this. And over here, I have the same vector. Over here, I have the same vector like this. And over here, they are like that. Same thing happens actually over here. And on the other side, I didn't do any negative values, I should have. What happens at minus 1, comma 0? The vector is minus 1, comma 0. So the vector here actually points in that direction. And if I am all the way over here, then it's a larger vector. So that tells you, if you think about this in terms of a dynamical system, if you start right at the y line, at the y-axis, you would never move. But as soon as you deviate and get a little bit in the first quadrant, for example, then you would just be pushed. So if you start here, you're always here. But if you start here, you would start moving in that direction forever. Okay? So this is what they mean when they say sketch vector field, it's nice to have some table of values. It's nice to come up with like what is the length of the vector at any point. Just so you know that this would be wrong if every vector that I drew had the same magnitude. Because this means that I'm starting moving like that and I'm accelerating as I go in that direction. If this is a force, what it means is that the acceleration is larger and larger and larger, so it would start slow and then like pick up and go really fast. Yeah, that's what this says. The magnitude of the vector will be the absolute value of x. So one thing is the magnitude of the vector, and another one the vector itself. So minus 1 comma 0 will go to minus 1 comma 0. So it's a vector that points 1 unit to the left. And its length is, in absolute value, the length is 1. So what happens in this other vector field? Let me, again, give some values. At 0, 0, nothing happens. At 1, 0, I'm actually at 0, 1. At 0, 1, I'm at 0, 1 is minus 1 comma 0. At minus 1 comma 0, I'm at where do I go? Minus 1 comma 0 will be 0 minus 1, and so on. If I do 2 comma 0, I go to 0, 2. So you can see that the length of the vectors in the field are the square root of minus y squared plus x squared, which is the square root of x squared plus y squared, which is the same as the length of the position. Okay, so the farther I am from the origin radially, the larger will be those vectors, and then there is something happening in the vectors. What is happening to the vectors? So this says that 0, 0 is there, no vector. But at 1, 0, I'm pointing to 0, 1. So I'm pointing in that direction. I already see that this is not going to look great. I'm going to put already something else here. At 2, 0 is there. At 1, 1, what happened at 1, 1? What is f of 1, 1? It goes to minus 1, 1. So over here, it points to minus 1, 1. So over here, it points that way. Over here, it points that way. Over here is pointing that way. You can see where I'm going. I don't want to draw the whole thing. Over here, we draw like that, and so on. Here, it draws like this. Okay? So what it's describing is some sort of circular motion that the whole plane is rotating, but the farther you are away from the origin, it's rotating at a higher speed. Okay? So if you want, it will just look like this. Like that. I know those are all vectors, but the farther you are from the origin, the bigger vectors you get. You get tiny vectors over here and larger vectors away from the origin. No. No, in this case, the f, actually, it does correspond to some derivative. I think you're thinking of a gradient vector for circles, perhaps, what you're thinking. So it is not a derivative. Right now, this vector field is just vectors in space, and it's telling me for every point in space, there's a vector, and it points in some direction. It has some magnitude. That's all it's telling me without telling me derivatives. But we'll see in a moment that I'm going to get vector fields from functions by taking derivatives.
What if f isn't a derivative?
It's a function. It's just a function for a vector is giving me a, for a point is giving me a vector. Okay? Now, since I was talking about the Artemis mission, so let's sketch the gravitational field or the gravity force exerted on a planet of mass m by a star of mass m located at the origin. So we have a star and we have a planet, and there is going to be a force. Now, the origin is at the center of the sun, and there's two forces of the same magnitude, but they're pointing in opposite directions. Okay, so there is a force going from the sun to the planet, from the planet to the sun, and the magnitude is given by this quantity according to the Newton's laws of gravitation. So what are those vectors? What I'm asking is what is the gravitational vector field on the planet, not on the star. So I want the vector on the planet itself. If it was here, it would be this one. If it was here, it's going to go to the sun. So it's all going to look like this, except that the r squared tells me that the closer you are, the bigger of a magnitude you have. Okay? But if you're really far, it's going to be a tiny magnitude, and it's not going to have a big effect. If you're really close, it's pulling you very fast with a lot of force. So what is this force? It's going to be a force pointing to the origin of that magnitude. So first of all, what I want is, so I have the position of my planet at x, y, z, let's say, and I want a unit vector in the direction of the origin, so that then later I can scale it by the amount of force given by the Newton gravitational law. So what is a unit vector in the direction of the planet? That would be r divided by its length. So that is the vector x, y, z divided by the length of the vector. Okay. So again, this is a unit vector from the sun to the planet. Okay? Because that is just the vector from 0, 0, 0 to x, y, z. But actually my force is going to be directed to the sun. So I actually want minus divided by its length. So it's minus x, y, z divided by the length. Okay? So this is a unit vector to the sun from the planet. So those vectors point in the direction of the origin. And now I want to scale it by the right quantity. So the right quantity, the actual force at x, y, z, will be the quantity that Newton tells me, so the mass of the planet, the mass of the sun, the gravitational constant, divided by the distance to the object squared times the unit vector in the direction that I want. This, what I've written so far, is just a number. It's the magnitude, and that's why I'm multiplying by a unit vector. So I have a vector of length 1, and now scale it to the length mmg divided by r squared. Okay? So now I multiply by my unit vector that I found before, like that. And what I get is that the gravitational vector field is minus mmg divided by the length squared times r, length cubed. Like that, okay? What does that look like in coordinates? That is minus mg divided by x squared plus y squared plus z squared to the 1/2 to the 3, so it's to the 3/2 times x, y, z. That's a formula for the gravitational field. And what does it look like? Again, in 3D, this is where the sun is, burning hot. And then everywhere there is a vector. And if you're closer, it's a larger gravitational force. And if you're farther away, it's less. Yeah, if you have, so just think in 2D. This is 2, 3. Okay? Say that's the vector 2, 3. The vector 2, 3 goes from 0 to 2, 3. But I want a vector from 2, 3 to the origin. So I want this vector, which is negative that. So minus 2, 3, which is minus 2, minus 3.
So what does timesing it by the
This vector has length the square root of 4 squared plus 3 squared. But I want it to of a certain length. So I want my vector to be exactly of this magnitude, which is what Newton tells me, right? And since I want it of exactly this magnitude, I don't want this vector to have a length that is going to ruin the magnitude. So I want it in this direction, but I don't want any more magnitude to come from this factor. So I divide it by its own length. So this is pointing in the right direction of unit length times this. Now it is pointing in the right direction and of length equal to this factor.
I meant, like, you know how m big mg over r squared, why did you make that specific r squared?
Oh, because here r is a vector. In all of our calculations, we said r was the vector, which is the position of the planet. So r is not a quantity, r is a vector itself. Okay. Very good. Okay. So now, as I said, there's something called a gradient vector field, which is that when we have a function, so if I have a function f that goes from R2 and it gives me one value in R, we already computed gradients. Remember when we looked at Lagrange multipliers, when we were trying to find maxima and minima of functions, we played around with gradients. And the gradient of the function was, in fact, a vector. And it gave me a vector of partial derivatives. What this tells me is that the gradient is actually a vector field that for every point in the plane is giving me a direction, or vanishes, or it gives me a direction. And remember, we'll come back to this, that direction was critical in finding maxima and minima, because we said, in fact, the gradient, or when we found directional derivatives, the gradient was the direction of maximum growth, okay? So if the gradient is the direction of maximum growth, and the maximum growth, the maximum rate of change, is the length of that vector, if I do minus the gradient, that is the direction of maximum decrease, and I know what is the rate of change that would be the maximum decrease, is the opposite direction of the gradient. But in any case, I can find for functions from R2 to R, or for functions from R3 to R, I can find these vector fields that are called the gradient vector fields. So let's do an example. So I sketch the gradient vector field on the plane for this function. First of all, what is the gradient vector field? it will be the derivative of f with respect to x, comma, the derivative of f with respect to y. The derivative of f with respect to x is 2x, and with respect to y is 2y. So what is, this is twice, this is a scaling of the vector xy. So what this is telling me is this is radial, it has a radial symmetry, and at every point the vector is pointing outwards with twice the length of the point itself, of the distance to the point itself. So if this is x and this is y, it's telling me that at 0, 0, it vanishes. At 1, 1 is a vector in the direction of 1, 1, but of length 2. Well, actually, what is the length? What is the length of the gradient? The length of the gradient will be the square root of 2x squared plus 2y squared, which is the length of 4x squared plus 4y squared, which is twice the length to the point. Okay, so this would be length 1. This is length or length 1 to the point, twice to the point. And here it goes like this, and here it goes like this. If you go up here, then it is, something like that, and so on. So everything is trying to go away from the center. Why is that? In terms of what I just mentioned, first of all, what is the graph of this function? The cross sections are circles, right? Because if you cross section at z equals 4, z equals 9, z equals, so those are the cross sections. For z equals 0, I get x squared plus y squared equals 0, so there's only 1 point. For z equals 1, I get a circle of radius 1. For the z equals 4, I get a circle of radius 4. So it is a paraboloid. Yes. Sorry. Yes. Very good. Like that. But in any case, it is a paraboloid like that. Okay? So what is the gradient field telling me? The gradient field vanishes at 0, 0, which tells me that I can't decide where to go for maximum growth. In every direction, there's maximum growth. Okay? But once I am here, the gradient field is telling me that if I go exactly in this direction, which this point is here, and it's telling me that if I go straight in that direction, that will be the maximum growth of the function. Okay? If I am here, you go here, it's telling me the gradient points in that direction. It's telling me that if I go like that, that will be the greatest growth. It also tells me that if I go in the opposite direction, it will be the greatest decrease. Because if I go in this direction, I'm going to directly to the origin. Okay? And that's important. In the applications, in both directions is important, but we'll see in a moment what I meant of the applications of the gradient field to AI. Any questions on this vector field? So the vector field of the function, you should, if the function goes from R2 to R, you should imagine it as its picture here is in 2D. For every value of xy, I have a number value of my function. And this tells me that if I am here, if I move in this direction, the values of the function will increase the fastest. if I go from here in this direction, which matches this, that if I'm here in values and I start moving like that, the values of the function will increase the fastest. If I don't listen and I go instead in this direction, then I'm going to go in this direction and I'm not going to increase at all. Okay? So it just tells me how to navigate in a graph. You know, this graph is very easy and we know what the shape is, but when you don't know much about the graph, but you somehow are able to figure out what are these partial derivatives, it tells you in what direction you could maximize, you could get some better return if you modify your function in that direction, or you modify the inputs in that direction. Let me show you, going back to the gravitational field, that the gravitational field is, in fact, like somebody mentioned, is that a derivative? It is a derivative. It is a gradient vector field. So if I take this function, it turns out that the gradient of this function is the gravitational vector field. So what does that mean? So remember that the, so what is that function? F of x, y, z would be mg times 1 over the square root of x squared plus y squared plus z squared. So I can compute the derivative of this thing. So what is a partial derivative with respect to x? The gradient in this case will be the partial with respect to x, comma, the partial with respect to y, the partial with respect to z. So I can compute each one of those and see what I get. It's a little bit easier to take a derivative if we write it as x squared plus y squared plus z squared to the minus 1/2. So that will be, take the derivative and I get mg and then times minus 1/2. Those, by the way, mmg, those are the initials of my wife. Mmg times minus 1/2 times x squared plus y squared plus z squared to the minus 3/2, and then times the derivative of the inside with respect to x, which is 2x. Okay, so what you get at the end of the day is minus mmg. This 1/2 and the 1/2 will actually cancel out, so I don't get any denominators here. Mg x divided by x squared plus y squared plus z squared to the 3/2. Okay? If I took the derivative correctly, that's what it is, and I think I did. And then you can take the same for the partials with respect to y. It's very symmetric. So this is y divided by x squared plus y squared plus z squared to the 3/2. And the partial with respect to z is also minus mg z x squared plus y squared plus z squared squared to the 3/2. But what was the force field itself? It's up there. The force field itself was minus mg divided by x squared plus y squared plus z squared to the 3/2 times x, y, z. So if you look at what are the components of this vector, this thing times x, that's the x component, which corresponds to what we got here. This is exactly the same thing. The y component would be this, which is what I get when I multiply this by y, and this component, which is what I get this by z. This, by the way, is it has a name. When that is the case, when you have a field, a vector field that is the gradient of a function, of a real valued function, then we say, or the physicists say, that it's a conservative vector field. And we'll see that we're going to do integrals of vector fields, and when it is a conservative vector field, then we have the equivalent of the fundamental theorem of calculus, which is the fundamental theorem of line integrals. Yes, so the question was, show that f is equal to the gradient of little f. So I took little f, this little f, translated it into coordinates, and then computed the gradient of f. The gradient is the partials, partial with respect to x, comma, partial with respect to y, partial with respect to z. So what I did is take partial derivatives of this function and make it a vector, and then check that that vector that you get is actually equal to the vector that we had for the vector field that is given by the gravitational force. Right. So as I said, the most important thing we learned when we're taking derivatives, directional derivatives, is that the gradient vector tells you the direction of maximum directional value, directional derivative. So the direction of maximal rate of change. And that is very important, as I said, in applications, because in general, we don't have a formula for these functions, but we can figure out what's happening locally, what the gradients are locally at certain places. So what happens in the training of an LLM, of a training of one of these AI models, is that you write a model that depends on two constants, say, okay, x and y, and then that model, you set it, let's set it, okay, somewhere here, where x is 1 and y is 5. Wrong choice of color, 1 and 5, okay? I set my model over there, and then we have what are called loss functions. So what's a loss function? I want to train my model to, I'm going to feed it a number of pictures of cats and dogs, right? And then the model is going to return, this is a cat, this is a dog, this is a cat, this is a dog, and then I count how many times it's failed. Now, if you do it in that way, if it's just a binary output, then there is no calculus to be done. And this was actually one of the big advances in the field, was to change that answer. We are not looking for the models to be always right. We're looking for a percentage of correctness. So that answer was changed from just being 0 to 1 to what's called a sigmoid. So it's instead of a 0 to 1, which would be a step function, it was changed to be a sigmoid, something like this, okay? And I don't work in LLMs, AI, so this is all very rudimentary explanations of what's happening. But once you have that sigmoid, now all the loss function is now a differentiable function, so we can do calculus. When you feed your model that we've set up with these parameters, 1, 5, you feed all those images, the model will say, this is 95%, I'm sure it's a cat, this is 0%, I'm sure it's a dog, and it will give you a bunch of answers about your answers. And that gives you a total value of like how right was it, or maybe you want to do the square root of the squares of all those values or something, just to do some parameter that will measure how right your model was, and that gives you a score. And now what you want is to change these parameters in the training so that I'm going to change the parameters a little bit, but I'm hoping that the next iteration of my model will be better at it. But I don't know the function that is this loss function that counts how many times the model was right or wrong. I don't know that function, but I can compute some partial derivatives. I sort of know what's happening at that point. So what we do is compute that partial derivative and compute the gradient. And the gradient tells me that I should go, maybe it's telling me to go in that direction, or maybe it wants to go in that direction, who knows. let's say it's going in that direction, the gradient. That's the maximum, that's increasing loss. I don't want to increase loss, I want to do the opposite, okay? So this is telling me that if I go in that direction, I increase loss, so I'm going to do the complete opposite, and I'm going to do in that direction instead. And what you do is simply replace that by this value, okay? So now instead of 1.5 in my parameters, I'm going to do here, and now it's going to be 1.5, 5.5 for my parameters for my model. And then you run the loss function again and see what's the score. It's a little less. The loss is a little less, not great. So you just keep doing that and just keep following the negative of the gradient. So if it told me there, now it's probably going to tell me to go here, to go here, to go here, until I reach this point in the model, which corresponds to this value of loss, which is a local minimum of loss. And that's the best I can do with that training because of the way I started the training. It led me there. It's a local minimum of loss. And now you have ChatGPT 4.3. Okay. And then you do this, you keep doing better and better training with lots of data. The problem is that there is like the massive amount of data you're training on. You need all sorts of linear algebra applications to do this training correctly. But the essence of how the models are trained is this gradient descent method to figure out what are the minima of loss functions. Now there is a lot, they say like, oh my God, mathematicians are done. There's so much work to be done, even in this area. We don't know what these loss functions look like. Nobody knows what the geometry of these loss functions are. We don't know that there is global minima. Okay, so we don't know if there's a global minimum. Maybe this shape actually keeps falling, and there is some way to keep descending, and there is no global minimum. There's something that is an impediment to having a global minimum, because we don't know if these functions are smooth. We don't know if these functions are what they are in reality. There's a lot of work, theoretical work, to figure out how to better, or maybe there's a better way of training this gradient descent. That's up to you to figure out. Okay, so it's up to mathematicians and up to computer scientists to figure out what's happening. But this happens in this vector field, and it happens in all sorts of other vector fields where we don't have enough data, but we can do this gradient descent to move around to figure out some local minima by following the track of minus the gradient. Okay. Some other example of vector fields is computing work. So what is work is the work done by a constant force in vector form. So if the force is just constant, and we displace an object from point P to point Q, then the work will be given by this formula. The force here is a vector, the displacement is a vector displacement, and the force or the work is given by a dot product of the two. Okay, if it is a linear quantity, if it's just a quantity and the displacement is a quantity, it's a product of two numbers. But if it's in 3D and you're moving in some direction, there's some force in some other direction, the force is, the work is computed via a dot product. Okay, so let me write here that this big dot there, that is the dot product of two vectors. And remember that in one dimension, I think in calculus 1, probably when you first learned about integrals in one dimension, if the force is variable and you're moving from point A to point B, but the force acting in there is changing with respect to time from time A to time B, then you can compute the work by doing an integral. Okay, that's not what I meant, but it's kind of nice. So you can compute the work by integrating the force along that path. So now we want to do work, we compute work in three-dimensional paths. So how do we do that? There is some work there's some force field, which is this vector field of forces. Then we have a path in 3D. And what we want to do is break that path again, use the Riemann integral trick. You break that path into little subintervals, approximate each subinterval by a straight path, and then in a straight path, we know how to do work, compute the work by doing an integral in that path, or doing a dot product in that path. So the work is going to be approximated by a sum of dot products times the length of that path in arc length. So when you pass to the limit, what you get is these formulas. That the work of a force acting on an object that is moving in some path, what you do is do the dot product of the force times the unit vector that is the unit tangent vector of the path times arc length with respect to arc length. What is that? Well, the unit vector, if r of t is the function, the vector function that is giving the position of the object, the unit vector is the derivative divided by the length of the derivative. But remember that arc length was the length of the derivative times dt. So these two actually cancel out, and you get a pretty easy formula, which is the vector field evaluated at points in the path times the derivative of the vector, of the position vector. And you can see already that this very much looks like a U substitution, right? Except that the thing inside is a vector. We're integrating a vector, and this is a dot product. So it's not quite yet that we can, like, out of the box apply the change rule or the chain rule or U substitution, but we'll get there. In any case, this is how you compute work. So let's do an example of computing work of a moving particle along a quarter circle under that force. So we're going to be moving from 1, 0 to 0, 1. So the first step is parametrizing that path. That is parameterized most easily by cosine t, sine t between 0 angle and pi over 2 angle. What else I'm going to need to compute the force? I need the derivative vector. So the derivative, or the derivative vector is minus sine t cosine t. I'm going to need the force evaluated at points on the path. That is, the x coordinate is x squared. So x squared is, I evaluate cosine t squared, comma, and minus xy. So minus cosine t sine t. That is the force evaluated at points along the path. Okay, so now the work is the integral over that path of f dr, which is going to be, I'm going from 0 to pi over 2, f of rt dot product with r prime t dt. So I need one more thing here before I compute integrals, is the dot product of f of rt times r prime t. That is cosine t squared minus cosine t sine t dot product with minus sine t cosine t. And if you do the dot product here, so it will be cosine squared times minus sine t plus minus cosine t sine t times cosine t. And overall, what I get is minus twice cosine squared t sine t. So that's the function that I need to integrate. Okay. So now the work, again, will be the integral from 0 to pi over 2 f rt dot r prime t dt. And that was the integral from 0 to pi over 2 of minus 2 cosine square t sine t dt. And what you want to do here is a u sub with u equals cosine t. So du is minus sine t dt. And let me just skip that integration. But if you do that integral with that u substitution, you end up getting minus 2/3. Are there physicists in the room? Is that good or bad? Is positive work good or is negative work good? If I'm trying to spend less energy to move this thing, which way do I want work to be? The positive means that the force is giving you some, for example, kinetic energy from whatever is causing the force to the object. A negative is that you are actually transferring kinetic energy from the object to the force field, right? So in this case, if it was a planet and an object, if it is negative, that's bad for you because you are actually transferring kinetic energy to the planet. So you're fighting the gravity of the planet. If you think about integrating gravity, what happens? That happens. In any case, we actually want, if we are trying to design a path, a flight path, we were to compute the work that gravity is doing on our Orion spaceship for this mission. If I compute all the work that gravity forces are doing, I want to try to maximize the work. I want to try to get something very positive in the total. So I'm using gravity, and I'm matching the kinetic energy of the rotation of the Earth to get in sync. So that first loop that is happening is just like we're matching the speed of Earth, and we're just using that kinetic energy of the rotation. The ship, when it starts, it's rotating with the Earth, so you don't want to fight that rotation and lose that kinetic energy. So you want to use that kinetic energy with you, and then use that gravitational force to slingshot, and then go all the way to the moon, and then use the gravitational pull of the moon to sling you back, right? But in general, you want this work to be positive. So how do we actually set up an integral that would describe this for a path? I don't know. I don't have an equation for the path. I would love if maybe I'll put that as some sort of extra credit packet. If you could come up with equations that describe this path in 3D, I would love to see some equations that actually sort of resemble what Artemis, the Orion mission is doing. But how do I set up the work doing that gravitational forces are doing on the Orion ship? So the force on the path it's going to be the sum total of the vector fields that are generated by gravitational pulls of Earth, first of all, then the moon, and to some extent of the sun. I don't know what extent that is, but let's just throw it in. There's no harm in that. So the first one, just remember that the gravitational force of one was gmm divided by r, the length of r cubed times r. That was the gravitational pull of one object. So I have g mass of the Earth, okay, divided by n times the vector. I want a vector. We have to decide where is the origin of coordinates first of all? Where do you want to put the origin? I don't think the sun has has a big role to play here, in fact, but I think the biggest pull here is going to be the Earth. So I think it makes sense to actually put the center of coordinates at Earth. So that means that RT is in coordinates with respect to Earth. So I want to do the vector that goes from the Orion ship to the Earth. So it is the position of Earth minus the position of Artemis, of the Orion ship, like that. And then in the denominator of that constant is the cube of the length of that vector. Okay, so I'm just going to write it like this, so you know where, in particular, where the constants comes from in the next two terms. So that one is just for Earth. Then I need to know the little m is the mass of Orion. Now I need to know what happens with the moon. So this is the mass of the moon. MM sounds weird, and I believe space scientists call the moon Luna, so let's put it on L. And then it's going to be, now we want a vector from our spaceship to Luna, and that is going to be the position of Luna at any point. You saw the video, the animation at the beginning, that that matters a lot. In these 10 days that the ship has been going around, the moon has traveled a big distance, so this actually does matter quite a bit. So what is the distance from here to here? And then you can see also from that image that, you know, the moon starts like way over here, very far at the beginning. So this at time 0, this is negligible. Okay, it's some very big denominator here for this distance. Okay, so that distance is making this almost negligible compared to the pull of the Earth. As we get to the moon, that's when you see like loop around this, because there was some other animation that I saw that actually had the vector of the pole. As it went around, it showed the two vectors. I don't know why that didn't show up in my history. In any case, plus, now the third factor is against the sun. So now I have to multiply by the vector, that is position of the sun minus the position of Orion, divided by the position of the sun minus Orion in length cubed. And you see that that is huge, so this denominator is going to be ginormous, but that is a very small contribution always. And that's it, because now I have set it up. This is the force, so this whole thing, the work is going to be from, let's say time is in days, from 0 to day 10, and it's going to be the force times r prime dt. And that's a number that you have to take into consideration when you are designing the path. You give me a path, I throw it in this machine, and it tells me that's terrible, we're going to have to spend all this fuel. Try to minimize this. How? The path will have constants. You can give me a path that is given by sines and cosines or something. I can put two parameters and then feed that into a gradient descent, just to see how to minimize or actually how to maximize this work, because we want very positive work so that we are receiving kinetic energy. Okay? So this is one of the things to have into consideration when you are flying and when you're designing the path. In this case, the unknown is the path itself, RT, and this is one of the quantities to compute, to perfect, to try to minimize the expense of the travel. Okay. So in general, these integrals of vector fields have that form. If you just have any vector field and along a smooth curve, By this, we mean this quantity, and which is computed like so. And let me just set this one up. So if we want to evaluate with this force and along a twisted cubic, so this is the RT is given, so I need to figure out what is the derivative vector. That will be 1, 2t, 3t squared for derivative. And then f of RT, if you plug in, what do you get? You get x times y, so t times t squared is t cubed. Y times z is t to the 5. And x times z is t to the 4. And FRT dot product with r prime. So you do the dot product of those two, and you're going to get 1 times t cubed plus 2t times t to the 5 plus 3t squared times t to the 4. That is t cubed plus 5t to the 6. And finally, I want to integrate this with respect to dr, and that is going to be the integral of that dot product we just calculated. The time is going from 0 to 1 of t cubed plus 5t to the 6 dt, which is an immediate integral, and the answer is 27 over 28. Okay. So if you are doing a line integral of a vector field, this is how you do them. I just wanted to point out, to finish, that in the previous lecture about line integrals, we computed integrals of this form, where we were just doing the line integral with respect to x. But if you look at what this means and what this means, they actually mean exactly the same thing. Because this would be, so if f is given by this formula, then this integral over here, what is the integral of p dx? The integral of p dx is precisely the integral from a to b of p of x of t, y of t, z of t times x prime of t dt, where that times is really times, no dot product. And when you are doing this integral up here, when you do the dot product, what you're doing is p evaluated at r times r prime t, do that dot product, and you are going to get x prime t plus then the second component, q evaluated at rt times y prime of t plus r times z prime of t dt. So this integral that we get here, it actually matches this kind of integral that we were doing before in line integrals when we thought about it in that way. So this integral can be reinterpreted, if you want, as one of these line integrals that we talked about, and that will give an interpretation to these kind of line integrals, and together with this and what we call the fundamental theorem of line integrals will allow us to do integration and also to figure out more important theorems about line integrals. Yeah, so we'll do that next time.